Next week we are going to have an online class. Okay, so don't come over. Okay, for next week I'm going to have an online class because I have some meeting outside the campus. Okay, 所以下礼拜就不要来上课。好，但是我会在那个用上网的这个形式。我们是不是做过一次？对哈，那应该是大家，我就会把那个 I will put the link in on our website so that you can connect anytime you like. Okay, so it's a recorded lecture, so you don't need to come to class. You don't need to watch it at the time of the class. 你可以随便你自己想什么时间来看都可以。好，没问题吧？好 ，and then the week after next we'll have the final exam. Okay, so in between now and next week, I will put out the preparation PowerPoint and also give you one more homework. Okay, the next homework you don't need to hand it in. Okay, 好，不下一个那个作业就不用交。I'll give you the solution right away so that you can practice at home. Okay, any question about the arrangement? Okay, so now the final topic about this semester, vectorial calculus. Let me tell you the objective right away. Our objective is actually, where is it? The objective is actually the Maxwell equation. Our 我们的目标非常的明确哈。Our goal is to transform and tell you how to write the Maxwell equation into a second form. Okay, I think you have learned already all the 4 Maxwell equation in general physics, right? 服务已经教完了嘛，对不对？对吧？哈。应该是教过了嘛，对不对？Okay, if you are not that familiar, I'll give you some in my PowerPoint some review. Okay. However, the left-hand side we call it the integration form or integration formula. Okay. For example, you probably still remember Gauss form at least. Okay. The other 3 probably is more obscure, but this is the first one. Is the Gauss law, 高斯定律。好，高斯定律。Okay, so our goal is to transform the integral formulation of the Maxwell equation into a differentiation form. Differentiation form in Chinese, 我把这个积分的形式写成微分的形式。Usually in general physics, we have to introduce the Maxwell equation in integration form because it's more intuitive to talk about the integration of electric field over surface or the integration of the electric field over a line, so-called line integral, because it's easier, more intuitive to teach in the freshman course. However, the left-hand side form, the integration form, is much more difficult to manipulate. It's difficult to calculate. Okay, it's easier to teach, but it's much more difficult to calculate. Therefore, in your second semester sophomore year course of electromagnetism, the professor will move right away into the differentiation form because it is easier to calculate in this form. However, in this form, you have to introduce new notation. For example, this is called curl, and this is called div, or divergence, or curl. Okay, you need new notation. Okay, so that's why it's more difficult to teach in freshman course. Okay, therefore, this is often done in sophomore year. However, we move the mathematical physics to freshman. Therefore, I propose I will do this transition in the next couple in today and next week. This mathematics is usually called vectorial calculus or vector calculus. Okay, maybe in your calculus is approaching this topic of vector calculus. In our course, in our textbook, it's in the section 3, but I personally prefer this Feynman lectures. Okay, of the Feynman lecture, the volume 2, the chapter 2 and chapter 3 entitled of differential calculus of vector fields and vector integral calculus. You can read these 2 chapters. I think that's my favorite. It's the best introduction to vector calculus overall. OK， 这是最好的两章，你可以学这个 vector calculus 向量微积分最好的这个读物。OK， the Feynman is a very intuitive guy. So when he introduced mathematics, it is full of insight and intuition. Okay, it won't be very abstract. However, after you learn from intuition, the mathematics is right there. Okay, so I just admire his style so much. So I have to recommend these 2 chapters in his lectures. You can read it in the next couple of weeks, or you can also do it in the summer. Okay, it's very good reading. It will prepare you for your electromagnetism in the sophomore. OK， 它会让你准备大2的电磁学。你们在大2的时候最难的可能会是电磁学，但不是我们的数学物理，会是电磁学。因为电磁学 again, so many mathematics and so many different notations. So you will upgrade your skill just one step right away. Okay, so therefore, if I were you, I will try to prepare myself for that upgrading by reading something like this. Okay, because yeah. And also, there's another very good lecture notes by Professor David Tong. It sounds like a Chinese name, but I don't know where it is from China. Okay. Anyway, David Tong is a professor in Cambridge, and he has a very comprehensive lecture notes covering everything in physics, from mathematics, from mechanics to electromagnetism. And these lecture notes just come out as books, but it's very expensive, so you probably don't want to buy books. But you can search the web. Oh, actually, the site is here. Okay, and you can find these lecture notes from his site. Okay, but if you are rich and you prefer books, yeah, the textbooks are available now. However, in his lecture notes, there is a couple of the lecture notes called vector calculus. It corresponds directly to what we are going to teach in the next today and next week. Okay, so you can consult these lecture notes. You see, for example, on the 3rd section, it's grad, diff, and curl. 梯度、散度跟旋度，你们的这个微积分是不是刚好要开始教这个了？梯度刚好教完了，对吧？好，所以 yeah, that's the exact same thing. Your calculus are covering at the moment. So that's the so-called vector calculus. Okay, so anyway, what is vector calculus about? It's about fields, or I should say, it's a function of space and time. Oh, so immediately to your mind, wave function, right? Wave function, phi, it is a function of x and t. So that's why we are going to this vector calculus, because we will very soon face function. We need to deal with wave function very soon in wave equation. Therefore, we need to know how to do calculus on functions of space and time. Okay, that's the key. And the so-called functions of space and time, there's another name for it. It's called fields. And the wave function are the simplest kind of fields, scalar function, because phi is just a number. It's just a number. Okay, so we usually call it a space scalar function. Okay, or scalar field. However, sometimes now, scalar field, the simplest example are wave function. Next is potential energy. Potential energy, of course, it depends on the location. Okay, so therefore it is also a function of space. Okay, and the next electric potential is another example of scalar function in space, scalar function. On the contrary, from electric field, if you find electric potential, you immediately know there are some other function of time we call electric field. Electric field is so different from electric potential in that the electric field is a vector potential. It's a vector potential. Okay, so therefore it's a space mapping to vector fields, to vector. So we call it a vector potential, vector field, the electric field. Here I list some of my PowerPoint transparency from the general physics course. Or if you are not familiar with, you are still feel that you are not familiar with the concept of electric field, you can consult it. OK， 这是我的这个普物里面讲到电场的这个部分，所以反白我就是在这边不讲，但是呢，如果你觉得你还都需要一点点的这个背景的知识的话，那你就可以看看这些部分，会介绍这个 electric field 到底是怎么一回事，那 electric field, the easiest way to visualize it is through the electric field line or called 电力线electric force line 好，那 I'm going to skip this part, but if you are interested, you can consult these background material. And okay, so now I'm going to introduce the differential formulation of Maxwell equation from the integral formulation. The key is that every function in space, we could do 3 different kinds of differentiation. Okay, in ordinary differentiation, we only have 1 differentiation. However, in space, at least we can take the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with z. There are at least 3 partial differentiation we can deal with. Okay, and for example, if in the case of electrostatics, the derivative of the electric potential is the electric field. Okay, so dV over dx is equal to E. However, in space, in 3D space, you would expect partial V, partial X, partial V, partial Y, and partial V, partial Z will be equal to the vector of E, electric field. Okay, but is it really true? First of all, you have to answer the question whether the 3 partial derivatives look like components of vector, but are they really a vector, first of all? And if it is a vector, is the vector equal to the vector of the electric field? That's my question. Okay. You have already learned from electrostatics that the electric potential difference is equal to the line integral of the electric field. 你们在进电学的时候已经学过这个公式了 ，OK？ 也就是这个电位的差，事实上呢是电场的线积分。By line integration, I mean I choose a path in the space and divide it by the path into small segments. For example, here I have a small segment of displacement I call ds. Because it's a displacement, therefore it's actually a function, a vector. Then I can take the inner product of the electric field at this point with ds, and then E dot ds becomes the contribution to the line integration at this segment. And you add up every contribution, it becomes an integration, an integral. Okay? So I hope this, and then if you do this, take a minus sign, then it will be equal to the difference of electric potential between P1 and P2. Okay, so that's the starting point of our discussion. That will be the starting point of our discussion. If you still don't understand this formula, please go back to the electrostatics. 在静电学里头，应该会 那普物的教科书里面应该会有这个式子 ，OK， 好，应该可以吧 ？OK， 好 ，so delta V is the line integral. I'll call it I'll say that the difference of electric potential equal to the minus line integral of electric field. Let me emphasize one thing. Here, I take the electric field and electric potential as an example to do the calculus, okay, and make statement. However, you will see that it does not only apply to electric field. Actually, it applies to any vector field, for example, magnetic field. Okay, so the next step, when I do every explanation, do any calculation, actually it applies to a general case. Okay, although if I simplify to electric field and electric potential, it feel more concrete. 好，这个例子呢看起来比较具体一点。好 ，it probably will help you learn what I'm talking about. Okay, however, you have to remember everything I say from this point on actually apply to more general case of vector field, not just electric field. Okay, 好，不是只有对电场来适用，其实任何的向量场都可以适用。So I'm going to derive if delta V is equal to the line integration of E, then E will be equal to the gradient of electric potential. So what I do is to introduce the concept of gradient. Okay, so now the derivation is actually very simple. I only need to apply this formula, delta V equal to the line integration of electric field, to 2 points, but they are very close to each other. Okay, so P1 here, P2 here. Okay, because they are so close to each other, in between, the electric field is almost a constant. Therefore, this line integration, you can just multiply by E by the displacement between the 2 points, delta R. So P1 and P2, the displacement or ds in the earlier notation, but in this picture I call it delta R. Sorry, the diagram come from very different textbook. So here is ds, but in this concrete case, I call it delta R, but essentially they are the same thing. Okay, and when P1 and P2 are very close to each other, the difference, the displacement, delta R, consists of delta X in this picture, delta X is here, delta Y, and delta Z is in this direction. Delta Z, okay? Oh yeah, delta X, delta Z, and delta Y. And therefore, the calculation is very simple for this simple case. It is just equal to the inner product electric field and delta R. So it is equal to minus EX times delta X, minus EY times delta Y, minus EZ times delta Z. It's according to the definition, right? Okay, so the difference of the electric potential between these 2 points could be written in this way if the 2 points are very close to each other. Remember, because they are close to each other, therefore I have only one set of electric field. Otherwise, the electric field could change. In the earlier case, if it is a finite path, then electric field could change at every point. But here, it does not happen because, again, P1 and P2 are so close to each other. Okay, so I can do this. Delta V could be written in this way. But those of you who have already taken the calculus, the professor has already covered the partial differentiation. This expression, the difference between the function, could be written in another form, which is partial V partial X times delta X, partial V partial Y times delta Y, partial V partial Z times delta Z. It's from calculus. Okay. If you still don't understand this formula, you have your professor covered this? If not, I actually has a very simple explanation here. Okay, it is actually an extension of the 中值定理. The difference between function is equal to the derivative times delta x. it's a simple formula from ordinary calculus. But now I can extend this formula to multivariable case. The case is simple. Now, x, if I consider the original point xy and at the adjacent point x plus delta x, y plus delta y, and you ask how much the function will differ from here to here, that is delta v. Okay, so this delta v could be written as v at this point minus v at this point. Okay, but I don't know how to calculate this, but I know how to calculate the difference between here and the difference between here. 可以吗 ？In Chinese， 我要算这一点跟这一点的函数差，我可以分两次做。我可以算这一点跟这一点的函数差，再算这一点跟这一点的函数差，加起来就好了啊。It's okay with everybody. So I can separate the difference between these two function difference between these 2 points. Between here to here and here to here. So I write this expression as v at this point minus v at this point. The first difference. And the second difference from here to here, here to here. The point is, in the first difference, only x change. Y doesn't change. Okay, so it's actually a function of x. So according to the theorem, I can write this as partial v partial x times delta x. Is that okay? Because in the first, sorry, I'm talking about this instead. So from here to here, y does not change, only x change. Okay, therefore I can write it as partial v partial x because this partial differentiation is defined as the derivative when y does not change but x change. Exactly the same thing here. Exactly the situation here. Okay, so partial v partial x delta x plus this and this. The difference between them is easy to calculate because here and here the x does not change. So it is equal to partial v, partial y. The definition is when you keep x not changing and change only y, then this is the derivative. Partial v, partial y times delta y. Okay, so I'm done. If I can calculate this, plus I can calculate this, the sum will be the difference between these 2 points. Okay. However, here, when you do the difference in the first place, the y position is y plus delta y, see? However, when delta y goes to 0, then y plus delta y just approach y. Simple, okay? So, in sum, the total function difference is equal to partial v partial x times delta x. This point, partial v partial y times delta y at this point. So I'm done. Okay, so I'm done. 所以呢，这个是一个非常非常有用的一个定理，好，一个函数的变化，你可以把它拆成对第一个变数的微分乘上变数变化，再加上第二个变数的微分乘上它的变数变化。那如果有第三个，那你就把第三个也加进来，所以这就是我们前面这里所写的 delta v partial v partial x delta y plus delta v partial v partial y delta y plus if there's a third coordinates, then it will be partial v partial z delta z. 都可以哈 ？Is it okay with everybody? Then if this is correct and this is correct, by comparing, we are calculating the same thing. So we compare the two expressions. It is easy to see Ex is just equal to partial v partial x minus sign. Ey partial v partial y minus sign. Ez partial v partial z minus sign. And we know Ex, Ey, Ez are components of a vector field. So it proves that this, and this are indeed components of a vector field. Okay, so I can write partial v, partial x, partial y, partial v, partial y, partial v, partial z in terms of a vector notation form. 我们可以把它写成一个向量的形式，因为它真的是一个向量 ，ladies and gentlemen. Okay, so this expression not only apply to the vector the electric field. Remember, in this page, I did not use the detailed property of electric field. 我没有用到电场的细的这个性质。The only thing I use is this expression. Okay, therefore, 我们刚刚所得到的这个结论，对任何的这个 phi 都是对的，对任何的 vector field 呢都是对的。好，总而言之，我把一个 phi 的 function 对 x 为分，把它对 y 为分，把它对 z 为分了以后，我就组成了一个 component of a vector. Okay, so 这一个我们给它一个新的符号。We give a new notation for this expression. We call it a gradient. A gradient. Because it is a vector, so there is an arrow on top of it to denote. This notation will give you a vector field. Okay, so gradient. So gradient. Sometimes we even, because it's a gradient, its gradient is a vector. Sometimes I treat the notation almost like a vector. The operation of the partial differentiation is a notation. Delta. Delta. Okay. Grade. Usually we call this, we pronounce this notation as grade. G-R-A-D, grade. So this notation is grade equal to partial x, partial y, partial z. Okay. Of course, this notation is only an operation. Therefore, it must act on a certain function. Therefore, when it acts on a certain function, it becomes a vector field. Okay. Actually, there is a theorem. If the line integral of a vector field A equals the difference of a scalar field, actually A is equal to minus grad phi. Okay, this is exactly the same theorem we have proven here. Okay, proven here. Here I only use the electric field and the electric potential as an example. However, all the derivation could be applied in this general case. Okay, if A is a vector field and its line integration is the difference of a scalar function, then A will be equal to minus grad phi. Okay, is that okay with everybody? Okay, so a fine example is to calculate electric field of a point particle. Okay, we all know that the point particle, the electric potential of a point particle is 1 over 4 pi epsilon 0 q over r. So we will have a problem in your homework. You can calculate the grad of V. You can prove that the grad of V is equal to this form, 4 pi epsilon 0 q over r squared r hat. Okay, so this could be proven in this case. Okay, here I also have some PowerPoint from my general physics course. You can consult. Okay, so gradient. Any question about a gradient? If gradient is okay with you, now up to this point, all the gradient is acting on scalar field. For example, phi, for example, V, electric potential. However, this partial differentiation could also act on another another vector function. For example, it could act on E. However, because there are 3 components of the gradient vector, and there are also 3 components of electric field. So when you put the gradient to act on the electric field, you must be careful about the indices. Okay, there are two ways to arrange the indices. One is to arrange the indices almost like an inner product. Okay, so while taking the derivative. So this is called divergence. The notation is grad dot E. It is defined as EX over partial X, EY over partial Y, partial EZ over partial Z. So the index is arranged almost like this vector and this vector are taking inner product. Is that okay? That's the definition. Okay, we call it divergence. I'm going to show you before you leave why this divergence is useful. But before that, is that okay, the definition? Again, what I'm doing is putting this partial differentiation to act on an electric field. After all, a vector field consists of three functions, Ex, Ey, and Ez. So I can take the differentiation, the partial differentiation on them. But however, you need to be careful about the indices. Indices means X, Y, and Z. 你的这个 X 跟 Y 呢，必须要弄得非常的刚刚好，那么它才会变成是一个有意义的东西。Okay, so one way is to put them such that it looks like an inner product. So Ex correspond to partial X, Ey correspond to partial Y, Ez correspond to partial Z. Or put in another way, I take the X derivative to Ex, take the Y derivative to Ey, take the Z derivative to Ez, almost like the gradient and the E are making an inner product. This expression is called divergence. Of course, you will say there's another way to arrange the indices, which is like a cross product. So, of course, the notation is grad cross E. And if you remember the definition of the component, it is the for the first one, it is the Z component, Y component, minus Y component, Z component. So it translates to this one. So it is defined as Ez over partial Y minus Ey over partial Z. So my way of remembering it is for X, it is YZ. For Y, it is ZX because XYZ, XYZ, there is a natural sequence between these three indices. Okay, so for the Y, it is the Z of the first component matching the Y of the second component. Oh, matching the X of the second vector. Okay, so this expression is called curl. We are going to cover this curl and tell you why it is useful next week. Curl. Okay, these are the two operations we can put on the gradient can act on a vector field. 可以吗 ？OK， 好，所以呢，因为你的这个 gradient 是一个 vector， 你如果要把它作用在一个 vector 场的上头，最重要的问题是，你怎样这些 indices 要怎么样子把它安排 ？OK， 好，那最好的安排就有两种的可能性，一个是把它看成是一个内积，一个呢是把它看成是一个外积。如果是内积呢，就表示第一个 vector 的 component 跟第二个 vector 的 component 两个是 match 的，所以 x match x，y match y，z match z， 然后加在一起。So I think this definition is clear. It may take a little bit time to realize the second expression. It is matching the indices of gradient and the indices of E in the cross product way. Okay, so if you maybe I should write down the A cross B, the component of X cross B here, so that you can compare each other when you study this transparency. Okay, divergence and curl. And divergence and curl can help us relate to the integration of vector field in space. Vector field in space, the integration of vector field in space has two different kinds of integration. First is the surface integration, and the second is the line integration. 线积分跟这个面积分。The surface integral is applied to Gauss law, and the line integration is applied to Ampere's law. Okay, so I hope you already learned the Gauss law and Ampere's law in class, in general physics class. Okay, so let's start with Gauss law. Let's start with Gauss law. Gauss law means when you calculate the electric flux, E dot dA. E dot dA means the flux we define as the flux of the electric field. And in notation, it is E taking the inner product with dA and taking the integration. According to Gauss law, E dot dA, the electric flux, is equal to Q over epsilon 0. Q is the charge inside the Gaussian surface you introduce in space. Okay, and because this electric flux is equal to the number of electric line, and therefore, if you calculate this, it is equal to the number of electric line leaving the surface minus the line, the line entering the surface. Okay, so if this Gaussian surface does not cover any charge, does not enclose any charge, then those leaving will be equal to those coming. Then for the two numbers equal to each other, they cancel out. Therefore, the electric flux would be equal to 0. 电通量永远是等于0。但是如果 if there are some particle inside the Gaussian surface, then it will not be equal to 0, and we can calculate it. It is equal to Q over epsilon 0. Okay, and therefore that's the essence of the Gaussian law. The Gauss law. The surface integration of electric field is equal to Q over epsilon 0. 这个是一个很简单的 review 就是 Gauss law 呢 in integration form integration form. So in the next 10 minutes, I'm going to show you that this integration formulation can be put even more succinctly into a differential form. Divergence E equal to rho over epsilon 0. Okay, that's the thing I'm going to accomplish today. 有没有问题？等一下我们就要把这一个方程式，这是一个积分形式，把它写成微分形式。The reason is, again, it is easier to calculate in this differential form. Okay. The reason is simple. Now, if considering a large Gaussian surface, and if I cut it into half, then the original surface is A plus B, and now I divide it into A and B. The point is the flux through the first Gaussian surface plus the flux through the second Gaussian surface will be equal to the flux through the whole surface. In Chinese, 你经过这个 A 的 electric flux will be equal to 就会跟经过这个 B 的 electric flux 如果把它加在一起的话，就会是等于整个 Gaussian surface 的 electric flux. OK, 为什么？照理讲，这中间还有这一面啊。A 的 electric flux 是经过这一边 ，B 的 electric flux 是经过这一边 ，A plus B 中间是有一个交界的。However, the electric flux in the 这个中间的这个交界，on the 这个 surface will cancel each other, because for surface A, the area is pointing this way. However, for B, the vector of the surface is pointing on the opposite direction. Therefore, when you calculate the flux, those pointing this direction will be cancelled out with pointing that direction. Therefore, on this surface, the two electric flux will cancel out. Okay, so that tells you the electric flux of the whole surface is equal to the flux over A plus the electric surface over B. Okay, there's another diagram if you want to look at this one. This is V. If V is divided into V1 and V2, then surface S is divided into S1 and S2. Then you take the electric field of S1 and S2. If you sum them up, those in the electric flux across this overlapping surface intersection, they will cancel out each other. Okay, so electric flux of V1, S1 and electric of S2, if you sum them up, will be equal to electric flux of S. Okay, so that means when add up the flux through SAB in the between will cancel, leaving only that through the outer surface, SA plus SB. And SA plus SB is just the original Gaussian surface. Okay, so that means you can, when you want to calculate electric flux through a finite Gaussian surface, you can divide the Gaussian surface or divide this volume into smaller cube, Because if you add up all the flux through these small cubes, it will be equal to the flux over the whole Gaussian surface. Okay, 好 ，in Chinese， 我现在如果要算这整个的Gaussian surface 的电通量的话，我就可以把这整个的体积把它切成一小块一小块一小块，那我就可以去算每一个小块的 electric flux， 然后把它加在一起。OK， 啊，加在一起了以后，它就会等于整个大的Gaussian surface 的 electric flux。这一点是最重要的一个 observation. This is the most important observation that will lead to our calculation. I hope everybody is happy with that. The reason again is simple because if you calculate the electric flux for the whole surface, it will be equal to the electric flux, the sum of electric flux for the first one plus electric flux for the second one. Okay, then let's calculate the electric flux for a small cube like this. I put it in the direction of x and y, this small flux. The calculation is simple if this cube is small. First, I calculate the electric flux on the right-hand side and left-hand side. Remember, the right-hand side is on the YZ plane, right? The left-hand side is also a YZ plane, but on X. And the second surface is at X plus delta X. Therefore, the flux through this first surface is equal to EX, X plus delta X, times delta Y, delta Z. This is delta Y, this is delta Z. So delta Y, delta Z is the area of this square, okay, of this square, the area. And then in EX is the magnitude of the electric field projected in the direction of X. Remember, what we are calculating is E dot dA. Okay, if A is in the direction of X, then what you get is EX times dA. dA, delta Y, delta Z. EX will be EX evaluated at X plus delta X. So, the electric flux of the second square. The electric flux of the first square on the left-hand side is the same as the second, except that the EX has to be evaluated at the position X because it's here. Okay, so delta Y, delta Z can be taken out. So this is essentially the difference between electric field EX at this point and the EX at this point. And we have done this 3 times today. So this is the function difference. The function difference will be equal to the derivative times the variable difference. Except that here it is EX is at that of phi. 完全一模一样的。OK， 好，这里是 EX 的差，在这个点跟这个点，用图来说就是这个点跟这个点 的 EX 的差。那 according to what I explained earlier, the difference between EX at 2 points equals the partial derivative over X times delta X. 这个是变数差，这个是它的导数，所以是导数乘上变数差等于函数的差。So exactly the same thing. Okay, but if we written this way, it will be partial EX over partial X, delta X, delta Y, delta Z. For these two surface flux through these two surfaces. And we have 4 more surfaces, top and down. I think top and down YX, yeah, top and down could be equal, written as partial EY, partial Y times delta X, delta Y, delta Z. On top and bottom. Again, it could be written as a difference between them, and it is partial EY, partial Y times this. And also the front and back. So put everything together. I hope you will convince yourself. We will have the same delta X, delta Y, delta Z for all 3 terms I collected here. And then I have partial EX, partial X, partial EY, partial Y, and partial EZ, partial Z, all add up. Ladies and gentlemen, this is the expression for divergence. So what I have got is that the electric flux through this small cube is equal to the divergence times the volume of this small cube. Sometimes we like to call it this way. The physical meaning of divergence is the flux per unit volume, because it's times the unit the volume, then you will equal to the electric flux. Okay, so sometimes we like to write it as the divergence of E is partial, is the electric flux over volume, delta V. Is that okay with everybody? So, if I have this expression, then I can, and I have already shown you that a surface, a volume can be divided into the sum of small cubes. Then I can add, when I want to calculate the flux over the whole Gaussian surface, I can divide it, the whole surface into small cubes. So that means that total electric flux over the whole thing will be equal to the flux of all the cube summed up together. And the derivation in the previous page have shown you that this small electric flux or electric flux small cube is equal to the divergence times its small volume. So divergence times volume sum over together, it is a space integration. It's a space integration or volume integration over divergence of E. So this is called the Gaussian law of mathematics. The flux of the Gaussian surface equal to the integral of the divergence of the space inside the surface, written in this way. Ladies and gentlemen, this is called the Gaussian law. And here I derive it as if it only applied to electric field. However, it actually applies to any vector field. This will be true. Okay. Therefore, the A dA equal to div A dV. This is called the Gaussian law, mathematical. 数学的高斯定律啊，数学的高斯定律，也就是任何的一个高斯面啊，任何的一个高斯面，当我要算它的这个通量的时候，它就会等于你在高斯面的里面算它的散度 divergence 啊 div， 算它的散度对里面的整个空间呢做一个积分，就会得到这两个竟然是相等的。OK， 好。So it means integration in the volume is related to quantity on the surface. It's very, very unusual in mathematics. So that's why this Gaussian law is very, very important. It's very important. Okay? surface integration is equal to the divergence over volume integration. So now come back to physics. This is mathematical Gaussian law. If we come back to physics, the physics tell us the surface, the Gaussian law tell us the flux over this small cube is actually equal to Q over epsilon 0. It is equal to the charge inside this small cube. Let's call it Q over epsilon 0. Okay? But the Q, if it comes from a charge density distribution, and if this Q is very, very small, then this Q charge is equal to the charge density times the volume. But earlier I have already shown you that the electric flux through this small cube is equal to the divergence times delta V. Then therefore this delta V cancel this delta V. We arrive at the differential form of the Gaussian law. Divergence of E equal to rho over epsilon 0. Okay. I apply the physical Gaussian law to the small cube, then we arrive this differential form of the Gaussian law. Remember, the difference between the differential form and integration form are huge. Remember, when we talk about the integration form, we at least need a Gaussian surface. And the Gaussian surface could be large, so that's why integration usually apply to an area or a cube. However, here, this formula, the divergence E is the quantity at the point equal to the charge density at that point. So this formula is a local equation. This equation for every point of particle is true. This equation is true for every point in the space. Okay, so usually we call this kind of law or this kind of equation a local equation. 在地的啦 OK, let me put it in Chinese. 这个原来的Gaussian law 在这里。原来的Gaussian law之所以不好用，是因为你一开始就必须要假设它是有一个Gaussian surface。那一个Gaussian surface， 除非是你是一个无限小的空间，要不然的话它一定是有一个大小嘛。所以呢，如果你还记得在学普物的时候，你大部分用到Gaussian law的时候，都是一个大的Gaussian surface。OK, so it involved the integration form involved the electric field at the various point in the space. When you do this integration, it involves the electric field here. You need information about electric field at the finite space so that you can calculate the electric flux of a Gaussian surface. Okay, and then you formulate a Gaussian law for the electric flux. However, if I turn it into a differential form, this is only a formula. This is only an equation. Here, it is only an equation applied on one point. 这个方程式它只存在于一个点上面，应该是说它存在于任何一个点上面。So 很多时候我们就把它叫做在地化的一个方程式。It's a localized equation. Okay, so it only involves the electric field or its derivative at one point, not the other point. Okay, so therefore it is much easier to manipulate this kind of equation. Okay, so put it more explicitly, this divergence is a function of space, and on the right hand side, rho is also a function of space. So the divergence at right hand side, and the charge density on the right hand side has to be located at the same point. So that's why I call it the equation locally. Okay. Okay, so in this page, I derive the differential form from the integration form. Next, I can also prove in reverse. In reverse, I mean, if I take this differential form as true, can I derive the integration form? Of course you can do that. It is even simpler because you can just apply this differential form of physical Gaussian law to the mathematical Gaussian law. Mathematical Gaussian law says the electric flux through a Gaussian surface equal to the divergence of this electric field over the space integration. Okay, you can simply plug this formula into the right-hand side. So the divergence of E equal to rho over epsilon over here. Okay, and rho over epsilon taking a space or volume integration must equal to the charge inside the Gaussian surface. Okay, so it gives you the electric flux over a Gaussian surface equal to the charge inside it over epsilon 0. That's the integration form of the Gaussian law. Okay, so I derive the differential Gaussian law. I derive the integration form of the Gaussian law from the differential form. In the earlier page, I derived the differential form from the integration form. So that means the two forms are equivalent to each other. 所以两种高斯定律，事实上呢是等价的，这样事实上是等价的，因为我可以从微分推导出积分的形式。前一页我从积分的形式在这里推导出微分的形式。OK， 所以这表示这两种形式在数学上完全等价。Okay, so using the same kind of argument, actually you can easily derive the Gaussian law for magnetic field. It does not just apply to electric field. If you applied it to the magnetism, the Gaussian law for magnetism, remember in magnetism, it is the surface of the magnetic field equal to 0 all the time. Okay, so that means the depth of divergence of magnetic field is also equal to 0. Okay, so that account for the first two equations. Account for the first two equations of the Maxwell equation. Here I have the integration form. Here I have the differential form. Okay, so divergence of electric field equal to rho over epsilon 0, and divergence of magnetic field is always equal to 0. Okay, so I finished the first two. Next week, I'm going to finish the second part, the curl. So I'm going to tell you the curl of the electric field is related to the line integration of the electric field. So use the very similar kind of mathematical argument we call Stokes theorem. Okay, called Stokes theorem. Okay, so that we'll do it next week. 那考试the final exam will only cover this week. Next week will not be covered. 下礼拜的东西就不会在考试里头了。Is that okay? Okay. 所以呢，我们只会考到这礼拜所讲的这个东西。I will put out a second problem set, a homework, but you don't need to hand it in. 不用交的习题，你可以稍微做一下练习。You can practice about this kind of divergence and Gaussian laws, things like that. Okay, 所以下礼拜就不用来上课。We'll have online class next week. We'll have online class next week. And then the week after next, we'll have final exam. Okay, so see you in the final exam. If you have any question, please let me know.